I want to thank the organizers for giving me this opportunity to give this tutorial. So I'll be talking about isomorph-free exhaustive generation and how we can combine this with SAT solving. So it kind of fits perfectly into the SC squared framework. So I've structured the tutorial in sort of three parts. First is looking kind of towards the past and give you a background of what isomorph-free exhaustive generation is, because I don't assume you have familiarity with this. And then I'm going to bring it into the present day, where I'll go over two applications of some recent work where we've brought isomorph-free exhaustive generation to SAT solvers and got some relatively nice results. And then at the very end of the talk, I'll kind of look into the crystal ball and look into the future, give you some musings on what I think. And my goal is by the end of the talk to convince you that there's some untapped potential here, right? I think that it's a really interesting area that can really push the state of the art in many combinatorial problems. So that's, let me know in the after section if I was successful with that. Okay, so let's just start. What is an isomorphism, right? I think most people are familiar with this, but just to define all of our terms. So isomorphisms, the standard example I'm going to be using is just graphs, right? Because they're nice, they're easy to draw. So here I have two graphs on the slide, right? On the left and right, they both have 8 vertices. I've even drawn them in the vertices in the same positions, but the edges, of course, look different. So it looks like these are different graphs, but if you give them to like a computer algebra system like Maple, call it like is isomorphic, it's going to tell you they're actually the same graph, just kind of in disguise, right? The vertices on the left, if you label them in such a way and then permute the vertices, the edges are, and you permute the edges as well, they're actually the same graph, right? So morally speaking, we should consider these the same graph, but what's the big deal here? The problem is if you're going to represent the graph in a computational format, you're typically going to do something like an adjacency matrix. So on the slide here are 3 examples. So it's a 0-1 matrix where you put a 1 in the ijth entry if vertex I and vertex j are connected. All right, so these 3 graphs you can see visually are all isomorphic. But then if you're just looking at the 0-1 matrices, it's not so clear, especially if you imagine your program has these large 0-1 matrices. How does it determine that 2 given matrices are isomorphic or not? So this is a famous, difficult problem. And the motivation for the tutorial is totally clear here, right? We want to do some kind of search on graphs, say. And the problem then is a given graph, if we're only considering graphs up to isomorphism, then a given graph has n factorial in general, different ways of representing it as an adjacency matrix, right? You just permute the vertices and you come up in general with a new 0-1 matrix that represents the same structure. So this demands something to be done about it, right? You have this n factorial factor staring you on the face. What are you going to do about it, right? N factorial, it grows faster than exponential. If you just put your head in the sand and pretend it doesn't exist, you're going to be blown out of the water by someone who actually takes action to limit this n factorial factor, right? So it's of utmost importance we do something about it in order to make our combinatorial searches fast and efficient. So what do we do? So this is a very classic problem. I'm just going to go over 2 methods of isomorph-free exhaustive generation, well known in the symbolic computation literature. And I can only scratch the surface of this interesting problem. I'm going to go over the first method called recorded objects. This is a kind of a folklore method. It's kind of the first thing that you might want to try. It's basically you take a record of where you've been. And then a more sophisticated approach called orderly generation is dependent on a notion of defining a canonical representative. It has a bit of an interesting history. So it was developed by the 2 gentlemen on the bottom here in the late 70s, and this was done independently. So Igor Ferchev and Ronald Reed, Igor being with the USSR Academy of Sciences and Ronald being with the University of Waterloo. And they both kind of had illustrious careers. This was over 40 years ago. Unfortunately, they both passed in the last couple of years, but as I said, they were well known in the combinatorics and discrete mathematics communities. Okay, so let's start with the recorded objects. This is the simplest method to describe. The idea is when we're going to be going and executing some search for some combinatorial object, along the way, we're going to be constructing intermediate objects. All right. And every time you see an intermediate object, you record it. Right. And if you find a new object which is ever isomorphic to something that you've previously seen and recorded, then you just reject it. Right. Because if this new object is isomorphic to the thing that you've previously seen, there's no sense in working with it again. All right. So here's a pictorial representation of how this method would work on graphs. So on the top, we have a graph with one vertex, then the graphs with two vertices, and then the graph with three vertices. And if you use recorded objects, and assume we work left to right here, then the first graph and the second graph are both new. The third graph is isomorphic to the second, so we reject it. The fourth graph is new, and then the fifth graph is isomorphic to the third, and then the sixth and seventh are isomorphic to the fourth, right? And the eighth is new. So in the end, we've rejected 4 out of 8, the 8 graphs on 3 vertices. And then you can see at the bottom, this is the list of recorded objects that you have to take along with you. So the point here is that if you go now to 4 vertices, you're not going to explore anything below the nodes that you rejected, right? Because those subtrees are going to be isomorphic to the subtrees which you are going to explore. So this is, it's a very powerful method because we're pruning off large parts of the search tree near the top of the tree, right? It's not like we're just, we've removed 50% of the objects, but that's going to cascade, right? Every level you do the same thing, and you're removing many isomorphic copies. Okay, so how would you implement recorded objects in practice? The main thing that you would need to do is do a lookup up to isomorphism, right? So you have to record the object you've seen, but you have to record its sort of isomorphism class. So I won't get into the details of how this is done in practice, but I'll just say, this is a well-known problem. For example, the standard reference here is in the journal Symbolic Computation from 2014. And for example, the Symbolic Computation library Naughty implements this sort of technique. You basically generate a certificate of the isomorphism class. All right, so we'll assume that we can get these certificates. And now, if we want to do a fast lookup, well, you can use, for example, a hash table for that, right? You hash the certificate, and then from the hash, you have some kind of a pointer to the original certificate. Okay, so when you're going in and doing recorded objects, let's say you find an object you take the certificate of the isomorphism class, you take the hash is not in the table. This guarantees that this is a new object, so we cannot reject it, right? If the hash is not in the table, it's new, so we add the certificate into the hash table. Now, if the hash is in the table, this is a bit more complicated because you would like to assume that you've already seen this object and then therefore reject it. That's not totally sound, right? Because maybe there was a hash collision. If you only compare the hash of the new object, then you can't make the assumption that this thing is definitely seen before. So in the case where there's a hashes match, you actually have to go to the exact certificates and compare the certificates to make sure the certificates are identical in order to remove the object and reject it, because you might have had a hash collision otherwise. All right, so this is one of the downsides of the method. You can't just get away with storing hashes. You do have to store the entire certificate. The upshot of the method is it's relatively easy to implement, assuming that you have access to an isomorphism generator, which you can call a standard library to do that. The downside of the method is, as I was saying, the certificates have to be stored in their entirety, right? So this is going to be not ideal. The certificates are going to be typically on the order, the size of them are on the order of the size of the object. And the real painful thing is that we're going to be generating basically like an exponential number of these things, right? There's so many intermediate objects typically in a combinatorial search. This table that restores all the recorded objects is going to grow quite large. And this also means, unfortunately, the method doesn't really parallelize well, because essentially, if you split up your search space across 1,000 cores, every core is going to need to have access to the same table of recorded objects. right? If they didn't, then they're basically going to be recreating the same search because every separate processor is going to be finding the same object in different guises. So you really do want them all to have access to the same table. And this doesn't make parallelization easy. Maybe your cluster you could work around that, but it's just not ideal. So this brings me to orderly generation, which is a bit more of a sophisticated method. So this is dependent on defining a notion of canonical, right? So you define one canonical representative of an isomorphism class, right? So you're just going to have one, then we're only going to accept the objects which are canonical, and we're going to reject all the objects which aren't. There's also a second property that you need canonical to satisfy to make the method work, and that is listed as point 2 here. If you're imagining the object in the search tree, if an object is canonical, then its parent in the search tree must also be canonical. So why do we want this? I think an easy way to think about this is to think in the contrapositive. If is equivalent to saying if the object is not canonical, then all of its children are not canonical. And therefore, by induction, all of the grandchildren are not canonical, and so on. So if you ever come across something which is not canonical in the search tree, you can immediately reject it because all of its children, great-grandchildren, everything underneath it is also not going to be canonical. All right, so this is why you need the second property, because if you didn't have this, then in general, you could have an object that was not canonical, which would then later extend to a canonical object, right? So then you wouldn't be able to reject it. Okay, so how can we define canonical then? So again, I'll go back to graphs, and let's say we're going to focus on the adjacency matrix of a graph, and we can define a canonical representative to then be the, say, lexicographically greatest adjacency matrix in that isomorphism class. So you have to come up with a way of, ordering the bits of the adjacency matrix. You can just take the rows and concatenate them, right? So you form a vector, 0, 1 vector, and then define the canonical representative as the greatest lexicographically vector in that isomorphism class. So as an example, these are the 3 isomorphic matrices we saw before. And the first is canonical because it has a 1 in the second entry. This has a 1 in the third entry, and this has a 1 in the sixth entry. So these are least or smaller than the canonical. Okay, so this is an easy definition. And let's see, if we draw the same table or pictorial representation as we did before, you see that the search looks similar, but we reject slightly different nodes. We still come up with the same 3 vertex graphs, now represented as adjacency matrices, but the representative is going to be different. So we reject the nodes 2, 3, 4, and 7, because those are the nodes that aren't lex greatest, right? So it's just, but at the end, we don't care about which representative that we choose as long as we get one from every isomorphism class, right? So this is another method that you could use to basically do the same sort of exhaustive search. How would you implement this in practice? Well, the primary subroutine you'd need in this would be to make a canonical check, right? This is a general difficult problem. People study the complexity of this problem. It's still, we don't know the best methods of doing this. I can say one thing though, right? Usually it's going to be easy to detect a matrix is not canonical, right? Intuitively, if you have a adjacency matrix, it's often the case you can just permute a couple of vertices, and then you get a new adjacency matrix that is going to be lex greater, right? This is the typical case. And so often you just find, and once you find one permutation of the vertices which produce a greater adjacency matrix, this is a witness that the matrix is not canonical, right? So often if you have a canonical checker, it's going to immediately terminate and just say non-canonical. But then the problem then is, what about the case where the matrix is canonical? In this case, you kind of have to go through every possible permutation, which is just, there's so many of them, right? You can do a bit of a clever thing and do some backtracking search here. So the idea of how you would test that a matrix is canonical is something like this. You come up with a permutation of the vertices, and you apply the permutation to the matrix, and you get a new adjacency matrix. And you compare the two, right? The new thing, if it's greater than the original, then this is a witness that it's not canonical. You can immediately terminate. This is the easy case. Usually in the case when it's smaller or equal, you can't do that, you don't know. So you have to backtrack, try a new permutation, and keep going until you've tried all permutations. So this is going to be quite slow to try every permutation. One very powerful insight is to note that you don't have to, you can often backtrack early. You don't actually have to fill out the entire new adjacency matrix, right? If you have, if you've permuted a few vertices of your graph and you get the high bits, therefore, of your new matrix, and those high bits are smaller than your original matrix, then you can immediately backtrack. You don't even have to fill in the rest of the matrix because of how Lex ordering works, right? It's defined primarily on the high bits. So this allows you to often backtrack early, so it dramatically speeds up the running time of this approach. But again, this is, this is a difficult problem. We don't have, it'll be relatively fast usually, but sometimes it'll be relatively slow. So that's the main downside of orderly generation. The upside, however, is that you don't have to be keeping around a table of recorded objects, right? Because every test is done locally, right? It's a local test of this specific adjacency matrix that you're looking at. This also makes the method parallelize easy, because if you just split up your search space into 1,000 subspaces, then and you look at a canonical matrix, right? It's going to be in exactly one of those spaces, assuming the spaces are distinct, right? So you don't have to worry about separate processors recreating the search, because the one canonical matrix is going to be accepted in exactly one of those subspaces. Okay, so let me just say some words about the SAT approach as well, right? Because we know that the SAT community also has done great work on doing combinatorial searches for objects. And of course, they have a similar problem. All right, they think about it in a bit of a different way. And in the SAT world, you typically focus on constraints, right? You specify your problem by a set of constraints, and then you give the constraints to the solver, and it finds objects satisfying those constraints. So when you have a search space which has a lot of isomorphisms in it, or a lot of symmetries in it, what you can do is add constraints, which is going to limit the space to hopefully a set of non-symmetric objects, right? So if you have the left and the right here, and the left is isomorphic to the right, just add a symmetry breaking constraint which focuses you on one of those two subspaces, right? So this is known as symmetry breaking, and it works very well in practice in many cases. The big issue is that it's often difficult to break some symmetries, right? It's often the case there's a lot of symmetries that can be broken easily by just some simple constraints, and then there's a lot of constraints which are just, they still exist, or there's a lot of symmetries which still exist in the search, and they're not so easy to add a constraint blocking them. As an example of this, again, going back to graphs, one thing that you can do is just assume that the rows of the adjacency matrix of your graph are sorted lexicographically. You can encode this into SAT easy. The problem is, although this is going to be beneficial, it's going to remove a lot of symmetry from the search. It doesn't remove all symmetry. As a simple example, these two 3x3 matrices are both isomorphic, and the rows of them are sorted in lexicographically increasing order. So this is the main problem with the simple approach of just adding a symmetry breaking constraint. So this brings me to the focus and the present day, the focus of the rest of the tutorial. And the remarkable thing here is that there seems to be almost no work using isomorph-free exhaustive generation, as I've described, inside of a SAT solver. And I don't know really why that is. I guess it could just come down to the whole reason for the SC² program, right? We have these two communities which both have decades of wisdom in them of how to go about solving this problem of removing isomorphisms. But really, you have the two hands. One hand doesn't know what the other's doing. Maybe that's the reason why it hasn't been done. I mean, I kind of scoured the literature looking for, the usage of isomorph-free exhaustive methods in SAT solving. I found one paper from the Journal of Symbolic Computation in 2020, and so they kind of made the same point. And so one of the goals of the tutorial then, and of course the whole SC² project, is hopefully this will change, right? Hopefully the wisdom of the two communities are going to kind of be absorbed by the other. Okay, so now this brings me to the present day. I'll talk about two applications that I've worked on recently where we found that using isomorph-free exhaustive generation in a SAT solver has actually been pretty useful. So the first application is to Lamb's problem. So this is work that I did as a postdoctoral fellow. So I spent several years postdocing around. So my 4 postdoctoral supervisors are this is joint work with them, right? They were listed on the slide here. So Kevin and Brett are professors in the math department at Carleton, and Ilias is at Wilfrid Laurier University, and Vijay is at Waterloo. And so this is a nice problem. It's kind of high profile. We won a best paper award for the work we did on this. So you know, we're happy that this sort of approach it worked. And so let me just give me a couple of minutes to just describe the history, because this is actually you know, I like this problem because it goes back all 2,000 years to Euclid. And so Euclid, you know, the great granddaddy of all mathematicians, right? He defined the axioms for geometry, and he said, okay, so he had 5 axioms. He says they characterize all geometric truths. So the interesting thing was the first 4 axioms were totally easy to state, and his 5th, this so-called parallel postulate, was much more complicated to state. So mathematicians were some of them were thinking, okay, well, why don't we just prove the parallel postulate in terms of the simpler axioms? This would, then we only have to have this nice, really simple set of axioms, and we have all geometric truths derived from them. So they tried to do this, right? They tried to do this for 2,000 years, and it turned out this was an impossible task. And this is now well known. In the 1800s, the work of Gauss and others found it's impossible because there are consistent models of geometry which Euclid never considered, right? Where parallel lines won't exist, but all his other axioms are totally satisfied. So in this slide, I've shown you 3 finite cases of that phenomenon. So these aren't geometries that Euclid ever considered. They don't look like geometries that you might think of, but you can actually consider them totally formally as structures which satisfy axioms of geometry, right? So they're given on the slide here, right? Any pair of points define a unique line, any pair of lines meet at a unique point, and then there's an order condition saying there's the same number of points on every line. All right, and then I've shown you 3 examples, color-coded to show you the points and lines in these structures. So you might have the question now, seeing these 3 examples, orders 1, 2, 3, for what orders do projective planes exist? And if you have that question, you're not alone, right? Mathematicians have studied this for hundreds of years, and we don't know the answer. Well, we know the answer up till 10. And 10 is Lamb's problem. So this became an infamous problem in the combinatorial community because projective planes are so easy to state, and 10 is a relatively small order, and no one could find one or prove one didn't exist until Lamb's a mathematician at Concordia University in Montreal, and he put together a team of programmers. This was in the late 80s, and they solved the problem by an exhaustive computer search. This was an enormous search. It was, they're using the fastest supercomputer of the day for months on end. So amazing piece of work. They got a lot of press for it because it was such a high-profile problem. Yeah, but at the end, some mathematicians were unsettled, right? Because this was, how do you know that their search program, which was the result crucially relied on this, didn't have a bug? And frankly speaking, we all know that computers, any software that you use, even if it's used billions of times, of course it has bugs, right? All software just has bugs. It's a reality. So the fact that you have like this search program run a single time, well, as they were upfront about, it's more than likely there was some kind of a bug. The question is, did it influence the final result? Did we actually miss a projective plane of order 10? So we basically, our result then was to certify Lamb's problem using a SAT solver, right? So you can generate certificates which can then be checked by a proof verifier. So if you believe in the encoding and you believe in the proof verifier, then you believe in the non-existence result. All right, and in fact, we actually did find, by looking at we didn't find the projective plane of order 10, right? We certified it didn't exist, but we did find some intermediate objects along the way that were missed by the previous search, right? So this really goes to show how important it is to have these certified resolution results when you have a non-existence result. So the point of this, I'll just kind of gloss over the SAT encoding because that's not the point of the tutorial, but it's simple enough to state. Even this is the main encoding just on the slide here, right? You come up with instead of drawing those nice diagrams, right, you use an instance matrix So you have a Boolean variable for every possible set of incidences, and then it's going to be a 1 if that point lies on that line, right? And so you have a bunch of Boolean variables here, and you have constraints which specify the axioms of the plane. You also have constraints which specify symmetry breaking, right? So that's also very important. But here's where it comes to isomorph generation. We found that even after adding the symmetry breaking constraints, lots of intermediate solutions still had symmetries, right? And this is the point I was making before. So what do we do about it? This is where the magic happens. We basically used the recorded objects approach because it was simple enough for our case, and even though we had to have this big table, it was sufficient. It didn't grow to a sufficient size that we had to look and go to other methods. So how does the method work? So as the SAT solver is running, it's finding partial solutions, right? It's finding an assignment to some of the variables which are going to define a partial projective plane, right? For example, I've drawn one on the slide here. It has 4 points and 6 lines, okay? And so it satisfies the axioms up to that point. So this can be given as a structure to a computer algebra system, and the computer algebra system can compute the isomorphism certificate of this thing, right? If the isomorphism certificate is new, then we keep the object around. Otherwise, if the isomorphism certificate has already been seen, then this is where the magic happens. We cut that branch out of the search tree, right? What we do is we programmatically learn a blocking clause to block the object from consideration, right? Because we already considered it. We already saw it. And so this is it's a really cool idea, right? This is based on a programmatic SAT solver developed by VJ, I guess, about a decade ago. And the idea is the normal way SAT solvers work is they're based on Boolean logic, right? And they use like the resolution rule to derive new clauses. Clauses are the fundamental everything is done in clauses in a SAT solver. They block parts of the search space via that. And but the cool thing is, normally the clauses are learned via resolution, but there's no reason, if you have some kind of an oracle like a CAS, this isomorphism certificate generator, there's no reason why you can't just add a clause into the SAT solver's database via this oracle. And this is immensely powerful, right? Because this is a clause that the SAT solver would never have learned via resolution. Okay, so how does this actually work in practice? Well, the hardest case, so Lamb's problem can be split into several cases. The very hardest case turns out to be, we have to find all possibilities for the first 19 points of the plane. All right, even after symmetry breaking, there are 56 million solutions to that. And it turns out there are only 500,000 of those 56 million are actually distinct up to isomorphism. So this tells you that there's a lot of unbroken symmetries in the search space, which are quite difficult to remove, right? No one knows like a simple symmetry breaking constraint which will remove those. So they still exist. The SAT solver is fine doing a lot of work repeatedly that it doesn't have to. And so what you could do is just wait to the very end of the search tree, right? And then of the 56 million, you've determined that you reject 55.5 million. But this turns out to be very slow. It's much better, as I was describing, as the solver is running, inject blocking clauses, which the way I think of it is at the top of the search tree, you're pruning away the large parts of the search. So instead of waiting until the very end to do the symmetry removal, right, the isomorphism rejection, you do it as you go, and this makes the search space much smaller. Now, there is a cost to pay, right? You do have to have the overhead of calling the CAS, storing the recorded objects, and doing the lookup, but the numbers speak for themselves, right? It was 150 times faster to do it with the isomorphism rejection with recorded objects rather than wait to the very end. All right, so it was a nice application of taking the recorded objects method from symbolic computation and then adding it to the techniques of the SAC community. So one other application I'm going to go over, this is the application of Calkin-Specker systems. And so I'm supervising a student with VJ, Brian. So this is a precocious undergraduate student, actually at the University of Toronto. He's doing, did great work on this problem. This was actually a problem given to me by VJ when I was a PhD student, and I kind of had it in the back of my mind ever since thinking about, okay, how can we use a SAT solver? I had this insight that we could use a SAT solver on this problem. This is a very interesting problem as well. It kind of so it was by John Conway and Simon Cochrane, and Conway being a famous mathematician who did the Game of Life. He did the studied the monster group. All sorts of his fingerprints are all over all this cool stuff in math. And unfortunately, he also passed away, I guess, at the beginning of the pandemic. But this really cool theorem that he had called the free will theorem, which is, you don't often hear of a theorem called the free will theorem, right? Something like this. But what it's saying intuitively is that if humans have free will, then elementary particles must have free will. All right. So very, very interesting. And it's based on a set of, this proof is based on a set of this existence of a configuration of three-dimensional vectors subject to some properties and also based on some laws of quantum mechanics that they assume. Okay, so let me show you what this set of vectors would look like. So this is from their proof. So this is the 31 directions devised by Conway. And they're the red dots in this diagram, right? So there's 31 red dots. They all define a distinct vector in three-dimensional space. So the assumption is then that if you're some kind of an experimenter and you have some kind of a particle, you're free to measure the spin of the particle in any one of these 31 directions. Okay, so this is the assumption. And by free, it means basically, free will. You have a choice that is not determined as a function of the past. And if you have that, and subject to the laws of quantum mechanics, then they prove that the particle is also free to choose its spin. So the result of the particle's spin in that direction is not dependent as a function of the past, right? This rules out, say, a lot of people have said, like quantum mechanics, there might be some hidden variables that you just don't have access to, but there must be some deterministic process that demonstrates the law of the outcome of this experiment, but in fact, it cannot be. If the experimenter was free to make the choice, then the particle, the outcome of the experiment, was also free. And so this is a proof based on the fact that it's impossible to consistently assign outcomes for the spin in all of these directions at the same time, right? There could not be any process that the particle could use, even if based on some hidden variable. There couldn't be any way of doing it. It's just, it's impossible, right? You can rule it out, assuming the laws of quantum mechanics. Anyways, this is a bit above my pay grade, right? I don't work in physics, but what I do, I'm interested in searching for combinatorial objects of this form. And so, well, first of all, here's the question. Conway and Cochrane, they had this Hawkins-Becker system with 31 directions, and they made their proof work. But they didn't show that this was, say, the optimal set of directions. Maybe it's the case there are a fewer number of directions which also have this property, right? And we don't actually know. This is an open question. The best known result is that must be at least 22 directions in any Hawkins-Becker system. Okay, and this was shown in 2016 via a huge computational search. Basically, what they did was they took a hypothetical 21 direction KS system, translated it into a graph, and then proved some properties about the graph must satisfy, and then ran an isomorph-free exhaustive generation over all 21 vertex graphs with those properties. All right, now the problem is this takes a very long time because there's so many 21 vertex graphs, even subject to the properties that they showed that the graph must satisfy. And so the computation took, I believe it was 300 PCs were running for 3 months. So and altogether like 75 CPU years, right? Huge computation. So this is where I started thinking, right? I was thinking, okay, we should be able to use a SAT solver on this sort of problem. So I kind of, with some cleverness, I sat down, I translate the properties that a KS graph must satisfy into Boolean logic. And then with Brian, he implemented that reduction and, have a program which generates the constraints, throw them at a SAT solver and see what happens. And as a researcher in SAT, you never know how the SAT solver is going to perform, right? It's like, I had some insight that maybe this is going to be a good thing, but who knows? sat solver, sometimes it works, sometimes it doesn't. It turned out to actually work really well. The intuition is kind of like there's lots of, they have all these messy constraints that a KS graph must satisfy. And a lot of them seem to be kind of contradictory, but it's kind of hard to prove something either way. But the solver somehow is able to use all these kind of constraints, which are mostly contradictory, to actually derive, to quickly rule out the possibility of many graphs, which if you do an isomorph-free exhaustive generation approach, are going to be considered, right? So the sat solver is able to really prune down the search, but there's a problem. And that's the problem is, even though we use some kind of symmetry breaking constraints, the sat solver is still generating many copies of the same graph because, as I mentioned before, there's some symmetry breaks which are easy to add, and then there's other isomorphisms which are very hard to break using constraints. So this is where the hybrid setting isomorph-free generation approach comes in. And this time we used orderly generation because we wanted to basically use parallelization, right? Because these spaces are so large. So we went with the orderly generation approach, but it's very similar to the previous. The idea here is that, okay, now we have this set of variables which correspond to a graph. And eventually, as the sat solver is going, it's finding partial solutions, right? So it's assigning some variables to true, some variables to false. When the variable is true, that's going to represent there's an edge in the graph. And once you have enough of the variables assigned, you have basically a complete subgraph. You have this subgraph in your hand, you can give it to a CAS. So here's the adjacency matrix of some subgraph, say. The CAS takes it and it does a canonical check, right? If this matrix turns out to be not canonical, which in this case it's not, right? We saw that this is a matrix that's not canonical because the one should be in the second entry if this is, because that's isomorphic and also Lex greater. So this is not canonical. And so then we learn a blocking clause, which is going to immediately just remove this object from the search tree, right? So again, it's the same process. And it's important to note, right, that the notion of canonical has to be defined so that this is never going to extend to any canonical adjacency matrix, right? Because of the way canonical is defined, this is not canonical, but also all extensions of this is not canonical. So it's safe to just remove it from the search space. So a bit of an optimization here. So in practice, you really do want to limit the number of canonical checks that you do, particularly when the matrix is more than likely canonical, right? You don't want to be given the same canonical matrix to the CAS because it's going to be every time you make that call, it's going to be there's an overhead associated with it. But one simple observation is that you can skip canonical checking whenever you like, as long as you don't block the object. Right, so what you can do is just whenever you see a canonical matrix, take the hash of it and then store that. And then when you have a new matrix, before you send it to the canonical checker, take the hash of it. And if the hash ever matches one of a canonical matrix, you just assume this new matrix is canonical, right? It might not be a completely safe assumption, but it's okay because you're not rejecting it based on that assumption. You're keeping it around based on that assumption. So if anything, you're just doing extra work, right? But it pays off because you're saving a lot of canonical checks. Okay, so that's just in practice, you can make it run a bit faster that way. So what are the results for the KS system search? So the idea is you look for KS graphs of order 16, 17, 18, 19, 20, and you just, the search space is increasing, right? So like order 16 runs in like a second, 17 in a minute, 18 in an hour, 19 in a day, sort of thing. But the speed up is also, it seems to be growing exponentially, right? And this is what you'd expect, because as the search space is increasing, the number of isomorphisms in the space is also increasing. So if you can block those isomorphisms and do it effectively, you're going to be getting a nice exponential speed up, right? And so this is what we observed. And then, so we actually went up to 21, and we resolved this in under a month on a single computer. So it was about 26 CPU days. So this was over 1,000 times faster than the previous search, right, which used this enormous cluster. It basically just goes to show you the power of combining these two approaches. And then, so here, for the first time, I can actually publicly state the result that we had here. We also did search for order 22 KS systems, and we didn't find any. So this took about 5 CPU years. This was split on a cluster. So unfortunately, we didn't find one. It would have been nice to find it, the smallest KS system, but at least now we have a new lower bound. The KS system must have at least 23 directions because there are none with 22 directions. All right, so this is still work that hasn't been published. So now let me move kind of into the latter part, just talk a bit about the future and what sort of things that we could improve here. So one big thing, which is particularly necessary when you want to go to these large orders and to search for these combinatorial objects, is parallelization, right? How do we do parallelization? And let me tell you first of all what doesn't work, right? So this is when I was thinking about, okay, how are we going to parallelize this search? My original thought was, well, let's search for all canonical subgraphs up to a given order, right? Some small order like 10, or 11, or 12. You find all canonical subgraphs up to that order, and then use that to seed the search, right? Split the search, right? If you have a couple thousand graphs, canonical graphs of those orders, you just give those to every graph to a separate core, and then have them try to extend, right? Extend that to a complete solution. And this turned out not to work because it was very unbalanced. Some of the graphs are going to extend to almost no partial solutions. Basically, the solver will just terminate unset almost immediately. And then others basically do all the work, right? There's going to be a couple that take up all your computation time. So it's really not a good way to parallelize the search. Okay, so that's not what doesn't work. So many people in the SAT community know of this cube and conquer method. This is just I consider like a miraculous method when it works. A lot of people, when they're thinking about parallelization, they're very happy if they can say, we've got a linear time speed up in the number of cores that we're using. With cube and conquer, amazingly, somehow you can, if it works well, you get a super linear time speed up. Like, this almost seems like it's too good to be true, right? It's impossible. The idea there is that it's often SAT solvers are very good at solving like bite-sized chunks, right? So you can imagine giving a SAT solver like an enormous boulder, and it can chip away at it and eventually reduce it to rubble. Or you give it as a bunch of like little pebbles, little cubes, and then have a SAT solver go at each cube individually. It's actually much faster to do the latter, even taking into account of the time it took to split the boulder. So this is just one of the things that SAT solvers are kind of counterintuitive, but it's much better to do the cubing or the splitting and then let the solver go, even if you're only using a single core. Now, this is still an active area of research, right? This is not something which is always going to work in every problem. And so we use cube and conquer in the KS graph application, as well as in the LAMS problem application. For the KS graph in particular, it wasn't giving us super linear time speedups. And I think the reason for this, and this is the kind of the open problem I kind of pose here, is we're not really taking into account the isomorph-free generation while we're doing the splitting. And it's not so clear how you go about to do that, because the way the splitting process works, it's kind of like using like a look ahead, right? You try to find the next variable, which is going to split the search space evenly, the most evenly, right? So you kind of do this look ahead to determine that. So it's not clear how you would use an isomorph-free generation approach to help do that, all right? But what we did was we took all the graphs up to, like, say, order 10, found all the non-canonical graphs, and then added those as blocking clauses and gave those to the splitting solver. It seemed to work a little bit, but I think maybe there's something that could be better done there, right? So, these two technologies there's still a lot of work to be done in trying to putting them together. So I think parallelization is a big thing where more work needs to be done. But let me end on a promising note. So I hope, as I said at the beginning, my goal is to convince you that these two approaches of SAT and isomorph-free generation are complementary and they deserve to be combined. So despite little work pursuing this, I think there should be more done. So this is kind of hopefully bringing shining some light on that area. And so the way I think of it as the last thing I'll say is, what we're doing is basically bolting together two technologies, right? They seem to work relatively well together because they're complementary, but really we're not designing, we're just taking one thing and plugging it into another. I kind of have an insight, maybe there's a better way to go about doing this, right? If we could really take the wisdom of the SAT community and the wisdom of the computer algebra community, and then design a system, a SAT solver, which could do isomorph-free generation sort of from the ground up, maybe we could get even better results, right? Rather than just kind of plugging this one method into the other. That's an open problem. So I'll pose that as sort of as a topic of discussion later. And then just the last thing, I hope I've convinced you that I really do believe there's great potential to be unlocked here, right? So I hope I've enticed some members of the audience to work on this problem. Anyway, so thanks everyone for your time, and I'll be happy to take questions.